Okay, so today we're going to look at, last week we looked at the sum and difference of functions. Today we'll look at the product and quotients of functions. Yeah, I forgot to post it Friday, but I did post it last night. So the product and quotients of functions, very similar to sums and differences of functions, except obviously for products we're multiplying two functions instead of adding them or subtracting, and for quotients we'll be dividing them. So the work here is very similar to the work from Friday. Basically the notation very similar, f times g at x. That notation just means take the function f at x and multiply it by the function g at x.
Are we always trying to find the y value?
Yeah. I mean, that's what functions are all about. And when we want to find the y values of f times g of x, it just means take the y value from f of x, multiply it by the y value of g of x, and you get the y value for f times g of x. So last week we talked about adding and subtracting. Same thing here, except we're going to be multiplying. So if you had a graph of both f and g, choose the x value, choose some x value, find the y for f, find the y value for g, add them together, multiply them together, and you get the y value of your product of two functions. I didn't leave enough space here to actually do this, I don't think, but I'll let you guys get caught up, and then we'll actually do the examples. So if we want to figure out what f times g of x is, we're actually going to take f at x and multiply it by g of x. In this case, we take a quadratic, we multiply it by a linear function, just x, and we end up with a cubic function. So algebraically, that's how you do it. Graphically, just like we did for the adding and subtracting, except we would multiply the y values instead of actually adding or subtracting them. If you were asked to find f times g at 2, you could actually do that in a couple ways. You could find out what g at 2 is, find out what f at 2 is, multiply them together, or you could just substitute a 2 into our function. We just found the function that represents f times g of x. So if we wanted to figure out that function value at 2, substitute a 2 in for x everywhere there's a 2. Good. And if you wanted to make sure you did it right, you could go back and say, hey, what's g at 2? Well, g at 2 is 2. And what's f at 2? 2 squared is 4, plus 2 minus 6 is 0. 0 times 2 is in fact 0. So we haven't made any mistakes here. Everything looks okay. And I want to show you how to use a graph. I think most of you are probably pretty comfortable with using a graph, but I want to just go through that process of showing you what that looks like, just so that you are okay with that. Oh, I meant to include the graph and I didn't. All right, so let's make a graph. What was f at x? It was x squared minus 6. Thank you. And g is x, right? I'm just going to grab a screenshot here. Oh, no. Really? That's not fun. All right, so here's the graph. Here's the graph of f of x. That would be this one here in red. Whoops. Here's the graph of g. And if we want to find the combined graph of multiplying f times g, same way that we did it last week, choose a value. I'm going to start here anyway. We're interested in the value of the function of f and g. Right. I mean, I chose that point on purpose because we know that the 0 of the linear function multiplied by anything else is going to give us a 0 here. So we know our function has a 0 value here. Here we have, what is this? This is 0 here times whatever the, oh, here it is. 0 times, what is that, at 1, 2? Is it, what's 0 times 2? All right, so far so good. What about this one right here? 0 times something over here is going to give us a 0. What kind of function should we end up with? It should be a cubic, right? So this is kind of matching up so far. We've just found some zeros. If you wanted to get a sense of what was going on in here, here we have, what is that, 2 and a little bit? Almost 2 and maybe even exactly 2.5, I'm not sure. 2 1/4, I guess. 2 1/4 times 2 1/4. Something bigger than 4, right? So we're going to get some number that's like up here. And then we could choose a few other points. Here we'll have a fairly large negative number, sorry, a fairly large positive number by a negative number. Yeah, so it's going to be negative. And we know that this is a cubic. A cubic generally has this kind of behavior. So we know it's going to look something like that. You know, we could go through and find a few more points and just multiply the y values together. But I think we probably have a good enough sense of what's going on here. Well, that's a good question. In terms of how exact you have to be, I don't expect you to go through and multiply every, you know, integer value, find the y values for every every x value that are integers. But I would say find the points. I probably should have done this one because that's a fairly easy one to do. Find the points that are matching kind of exactly and go from there. So say that again. Yeah, it's possible. Yeah, except in this case, not really, because if it touches and goes through one of the zeros, then it's going to have to come back, and we'll have one more max or min than we should have for a cubic function. But if it were another function, yeah, it's possible it could just touch and come back, which is why you want to go through this process of checking. Yeah, because 0 times anything else is still going to be 0. So all of the zeros of f and g actually become zeros of the original function. So when we did that matching of functions last week, that may have come in handy, you know, where we looked at the graph and the equations and tried to match them. That's a clear indication. If the zeros of both your original functions are zeros of your new function, then that's a clear indication that there's multiplication. All right, and the other thing that I wanted to say here, we talked last week about domain. The domain of f times g of x basically are the points. Hey. Yeah, come on in. Hey, welcome. Yeah, come on in.
What are we doing?
We're doing. Anyway, the domain of f times g of x, same thing as last time. It exists wherever there's an intersection of the domains of the two functions f and g. So have to look at the overlap.
Any concerns?
No, did we pass? We did okay?
Oh, yeah, we can ask Mr. Manager. He'll tell us later.
All right.
Okay, thank you.
Yeah, no problem.
So wait, I mean, I didn't hear any of that.
Sorry. The domain of this function f times g is the overlap of the two domains. So whatever they have in common. And I don't know if I did. I think I did this last week. I guess you weren't here. Yeah. Is if you think of the domains as a Venn diagram. So this is the domain of f, and this is the domain of g. This intersection, what they have in common is going to be the intersection. That will be the domain of f times g. What's that? You like that one too? Yeah. So the other thing that I said is that if, let's say that f was defined here for x values, you know, from whatever value this is to the left, and g was defined, let's say from here this way. I kind of wrecked this, but whoops, that didn't work. So f is here and g is here, then the combination, wherever the overlap is going to be your domain of f times g. And that was the same with addition and subtraction. So that intersection of domains is kind of an important concept. Good question. What's the domain of the linear function, the straight line, g? Anything. What's the domain of the parabola? Anything. So the domain of this right here, so the domain of, and I'll just write down here f times g, is just that x is an element of the reals. It can be anything.
Now, how does it work?
Yeah, it's true, because here the range, well, the range of the linear function was all possible y values. The range of the quadratic, though, wasn't, right? There was a minimum here. But the resulting equation was a cubic. It goes off forever in both directions. So in that case, the range of, in this case, the range is just that y is an element of the reals. So you basically have to look at the x values that you have and look at what's that going to do to the y values. So if instead of, not that this would have happened, but if instead of having, you know, a quadratic here, if we had some other value like a cubic, or not a cubic, a square root function, we would know that the square root has to be positive all the time, and this could be anywhere, so the domain is restricted to the positive x values. So we would look at, well, what happens when x is 0 or close to 0? and what happens when x is really close to positive infinity. Like kind of look at the endpoints and see, because that'll give you a good sense of what's going on. Is that okay? And then we can move on to quotients. So quotients is just dividing two functions. We've kind of looked at this already. We did rational functions. If you remember, the definition of a rational function was that it's basically one function divided by another function. So, you know, this isn't anything terribly new. But now we're going to actually do it instead of one polynomial function divided by another polynomial function. It could be any kinds of functions. So the notation is similar. F divided by g of x is equal to f of x divided by g of x. Yes, so division in order matters, right? 1 divided by 2 is not the same as 2 divided by 1, and the same applies for functions. And so we can do the same thing graphically. We could graph f, graph g, find the y values, take the y value for f, divide it by the g value, sorry, the y value for g, and get the y value for f divided by g of x. And so there's a bit of an example here. F of x is 3x, g of x is 2x minus 1. In this case, two functions are linear. And we're going to divide the two functions. So we would do that algebraically. And some of you might start to recognize this. You know, this looks a lot like the rational functions that we did. So we would be able to figure out a lot about this graph without having to graph it based on the work that you did with rational functions. So that's another reason why this is a good unit to finish with. It's kind of a review of all of the different functions put together. We'll talk about some of the characteristics of this in a little bit, but first let's get through this part. How do we evaluate f divided by g at 2? Yeah, that's right. You just plug a 2 in for x. I know you guys are all busy writing. And then we can evaluate that. That's, what's that, 6 over 3? This happens to be 2. How would you propose we simplify? Oh, okay. If you can, then yes. I mean, you want to make it as easy to deal with as possible. If you can, I know a lot of you are probably looking at this saying there's an x in the top and an x in the bottom. Why don't we just divide by x? But don't forget, you can't divide across the minus sign here. But if it had been sort of 3x over 2x squared minus x, then we could factor out an x and divide the top and the bottom by x. That would certainly work. And we should do that whenever we can, sort of like reducing fractions. Now, what do you think's gonna, we've talked about the domain of all these other functions. Any guesses about the domain of f divided by g of x? There will be an asymptote. How is the asymptote created? Right, so if the bottom is equal to 0, we have some issues. So there will be an asymptote, but other than that, the domain of the division of these two functions is going to be, again, the intersection of the two domains. So it's basically the intersection of the domains plus any restrictions created by the denominator. So we've created a denominator down here. Obviously, there's some value, maybe a half, that if we plug in there, we're going to get a 0. So we have to be aware of that. But other than that, the domain of f divided by g of x only exists where both of them exist and where g of x is not equal to 0. So that's the one extra stipulation that we have to worry about when we divide two functions. We have to just worry about the denominator equaling 0. Well, there will be, in this case, there will be a horizontal asymptote, and maybe it's probably worth talking about that just so that we can go ahead and provide a little bit of review. You know, the question didn't say to sketch this, but we could sketch this. So if you were asked about the domain and the range, you could actually give an answer based on the sketch. So how would we go about sketching this function right here? A table of values could work. Hopefully we can, well, I'm just worried that with a table of values, we're going to miss something, right? If you try to do a table of values with the parabola, but you only get like the right side of the parabola, it might look kind of like a straight line, depending on where you've got your values. So instead of using a table of values, what else could we do? Yeah, you could certainly draw the two different graphs, which would be easy enough here, two linear functions. How else could we do it? It's a rational function. We know that it probably has a vertical asymptote somewhere. Where would that vertical asymptote be? It happens when the denominator is equal to 0, right? So 2x minus 1 equals 0, and x equals a half. So we know that there's a vertical asymptote there. What about horizontal asymptotes? How do you find the horizontal asymptote of a rational function? Say that again? Nope. Divide by the highest power of x. What's the highest power of x in this function? X. So when we divide by the highest power of x, we get 3x over x. And then all of that's going to be over 2x over x. Whoa, sorry. Minus 1 over x. And remember, we're looking at what happens as x gets really big in the positive direction or in the negative direction. 1 divided by a really big number is essentially 0. If x gets really big here, we take 3 times that number and divide it by that really big number. That's going to go to 3, and this is going to go to 2. So the horizontal asymptote here is just going to be y equals 3 over 2. John brought up a good point. He said just set the top equal to 0. What does that give us if we set the top equal to 0? It'll give us the zeros, which might be helpful as well, right? So let's do that. Yeah. 0 is equal to, I guess it was 3x, right? I'm going to sketch what we have. Oh, because if you mean this part right here, if we sub in a really, really big positive number, so sub a million in here, 1 divided by a million is a pretty small number, right? It's not equal to 0, but it gets closer and closer to 0. So that's going to give us an indication of where that asymptote is. We said there's a vertical asymptote at x equals 1/2 right in here. We said there's a horizontal at y equals 3/2. Some of you might call that 1.5. You know that there is an x-intercept at 0. I guess that's all we need, right? If this is the asymptote, we're going to head off like this. If we really, really wanted to be sure of what was happening here, we could test for a really big negative number to see whether this was approaching from below or above. Well, we know that the intercept is here, so the graph has to be in this section, right? If it were up here, then it wouldn't go through the origin. So we know that it's down there. There is a possibility that it could do this, come up and come back down. It doesn't kind of look like that, but we could test, sub in a really big negative number, and by really big, I'm going to say -10. There probably are. I haven't seen any of those, but Yeah, it probably could be, but yeah. But certainly you could have this as well. And we can just test. So take our function, which was up here, sub in negative 10. 3 times negative 10 is negative 30. And then 2 times negative 10 is negative 20, minus 1 is negative 19. So negative 30 over negative 19. It's positive, we know that for sure. But again, we don't want to see if it's positive or not. We want to see, is it above or below this horizontal asymptote? So if you do 30 divided by 19, what do you get? It's above 1.5? Interesting. Did I do this part right? I just expected it to go from below. Negative 10, so 3 times negative 10, that is negative 30. Oh yeah, negative 20, take away 1, sorry. That's better. Should be negative 21. So then we know for sure it's not the red line here, it has to be the green line. And then let's see how much you remember. How do we figure out what the rest of the graph looks like? We know that the section on the left, right, so if you look at the vertical asymptote, on the left of the vertical asymptote is, the vertical asymptote comes from, I should write this equation down over here so I don't have to keep scrolling up. There's 3x over 2x minus 1. We know that the vertical asymptote comes from this, from the denominator, the roots of the denominator. There's only one root. And in this case, it's not squared. So the behavior on opposite, the fact that there's only one of them means that the function heads in opposite directions. So if the function is headed towards negative infinity on the left of the asymptote, that means on the right it has to head towards positive infinity, which means it looks like this. And again, we could test a really big positive number to see whether we cross the asymptote, but it's probably not likely. In this case, it's a fairly simple function, right? So it's going to be the same there. So then if you wanted to talk about the domain and the range.
Wait. So for finding out what the other half of the graph looks like, did you always use the denominator?
Yeah. And remember, just as a bit of a review, if this had been a 2x minus 1 squared, that would mean that on both sides of the asymptote, we'd head in the same direction. So we figured out one side, and then we look at the nature of the roots for the denominator to figure out what's happening on the other side. Yeah, we called this a simple root, and we called the other one a double root. So if it's a simple root, they head in opposite directions. If it's a double root, they head in the same direction. A triple root is the same as a simple root. So the even numbered and are the same, and the odd numbers are the same. Yep. Yep. So now we can look at this function and talk about the domain and the range. What's the domain of this function? We probably didn't have to graph it to find the domain. But yeah. So the domain is the intersection of the two domains, the 3x and the 2x minus 1. Well, this is defined everywhere. This function is defined everywhere. So is this one. So that means that the combination, the division, is defined everywhere except where g of x is equal to 0. And that's what we found here. So the domain is that x is an element of the reals such that x has to be, sorry, x cannot equal, what was that, a half? And the range, what's the range of this thing? Yeah, I think it's 1.5. Yeah, it was 3 halves, right? I know what you meant.
What is the crossover?
If it crosses over, then it can be that thing. Yep. Yeah, that's right. Remember, the horizontal asymptote describes end results. The function's allowed to cross it as long as it comes back and approaches it. Then everything works. Right, in grade 11, you don't cross it. I don't think there were any that you crossed. Yeah. I know it's one of those things that we tell you, you know, you can never cross a horizontal asymptote, and then you get here, and it's like, nope, you can. Well, you would have, because you would have looked at the function y equals 1 over x. It has a horizontal asymptote. Oh, well. And I think that's it. Yeah, that's it. So I think your work for today then is this bit right here. I think, yep. And I'll just add that in the note here.
Why don't you just look up your
Yeah, just for anybody that's not here today. Yeah, there should be. Should be audio as long as I turn the microphone on. You can actually take question 3 off. So there's only 2 questions that deal with quotients for you to practice with, but you get the idea.